In this example, we're looking at a computer system where we've got a lot of heat being generated by our processor, and we need to dissipate that. So in this case, what we're going to do is use a fan-forced heatsink system, and then we're going to use a heat pipe to transfer the heat from the processor to the heatsink. The Flow electronics module gives us some great capabilities to improve the performance and how we can calculate that. First element is in accurately modeling the heat generation from the processor. We have what we call a two resistor component, which is a much more accurate way of representing the heat being transmitted through the upper and lower surfaces through to the PCB board as well as to the heatsink layer. And Flow comes with a wide array of predefined processors or semiconductors to choose from, and all we have to do is really specify how much heat is being generated. Another great thing about Flow and the electronics module is the wide array of built-in materials. So for the conductive bonding paste, we've got choices from a wide array of different companies, as well as standard sorts of materials like aluminum, copper, and so on. To represent the fan system, we don't really need to model the airflow going through the fan because that's very well documented. So we're just going to define what the flow rate of the fan is and have that at the exit to then blow over the heatsink and then exit out through the vents. The heat pipe is a very efficient way of transferring energy from one point to another, or dissipate heat. All you do is specify the contact surfaces where the heat is being applied, and then the faces where it's going to be distributed. And then you've got the thermal resistance of the actual unit, which is fairly low typically. And heat pipes typically contain different sorts of liquids to help in that transmission, and they don't give off very much heat along the length because of the way that's being conducted. So let's take a look at the results for this system. We'll just do a section plot through the results. You can see for the overall system, the peak temperature in this case is 90 degrees. Ideally we want to keep the chip below 70 degrees, so you can see here with our 10 heatsink vanes, we're not really doing an effective way of dissipating that heat. If we move in closer, you can see that as the heat is coming out of the vanes, they are slowly heating up the air and then it will exit the system. But close to the exhaust from the fan, you see there's not much temperature increase in the air. So we can see that we've got a problem, and of course we can look at it at any position through the structure. So you can see towards the top there's not that much to worry about temperature, but as we go back down and we slice through the actual processor, that's where our peak temperature is, as we would expect. Flow provides a lot of tools to help us identify that. For example, we can pick particular bodies and find exact numerical values as well. In this instance, we can see that for the processor chip, our maximum and minimum temperatures range from 80 to 90 degrees, so that's definitely well above our 70 degree range. Now we could go through and try a variety of different configurations. So for example, 50 fins, and I'll show you the results for that just as a comparison. So you can see here the peak temperature is about 62 degrees, which is a lot better. And if we look in closer, you can see we're getting a lot more heat into the air as it's dissipating through the system. So we're transferring a lot more of the energy. Now, if we wanted to find the optimum solution, that's where again flow simulation has a lot of great capabilities. We have the ability to actually do a parametric study, which enables us to either manually build up what we want to optimize, or in this case I've predefined one and saved it, and we can go back and look at the different steps. But all we do is we specify a parameter. In this case we're using the pattern value for the number of heatsink vanes, and we're driving it from a range of 10 to 50, and then we're setting the goal of our temperature of our processor to be as close to 70 degrees as possible, and it's got to be within accuracy of 1 degree. Flow will then go through and run multiple iterations, and it can even create a study for each one of those iterations to achieve the optimum solution. It takes a few hours to run that, when you start doing more complex models. But here we've got our final solution, which is actually with 29 vanes. So let's take a look at the section plot through the system. So you can see here our peak temperature is 69 degrees. And again, it looks like we're getting good heat transmission through the structure and being dissipated out into the air. Again, go to our volume parameters to double check exactly what's going on in our chip. And again, we can see our minimum and maximum ranges from 58 to 69, so we're right on. So it's done a really good job of optimizing that. We have lots of other things. For example, we can also look at the results on the solids. So you can see in here, there's our red processor chip, since that's the hottest point. Of course, we can also do things as add flow trajectories. And we'll just do some arrows and show the temperature. And so now we can see those where the airflow is going. And of course, as we did with the section plots, we can animate those as well to see what's going on. One of the powers of flow simulation is the ability to get accurate results even with a relatively simple mesh. For example, if we show our section plot here, and we can actually show the level resolution on this model, so you can see that's the level of mesh resolution used for the default analysis. But it has a lot of built-in capabilities for refining calculations automatically around thin walls, like between the vanes in our heatsink. Now I've got a much more refined model here, and we'll look at the results of that as a comparison. I'll just hide that one. And when we turn on the mesh for that, you can see here we've got a much more refined result, but again our peak temperature is 69.14. We go back to our coarser model and it's 69.04. So it came out with a very close result. And that's because of the built-in quality of the SOLIDWORKS Flow Solver. It makes it very accurate even with a relatively coarse mesh. So you can be very confident in the results that you get out of it without having to spend too much time refining the mesh in a lot of locations. So this just demonstrates the great capabilities in the electronics module in flow simulation.